Photoelectric Effect by Jose Garcia and Chastity Barajas. What is the photoelectric effect? The photoelectric effect is a phenomenon in which electrons are emitted out of the surface of generally a metal in response to the incident of light. How does it work? When light hits the metal, the energy contained by the incident of light is absorbed by the electrons. The energy absorbed allows the electrons to be emitted from the surface of the metal. Since the late 19th century, physicians such as Heinrich Rudolf Hertz, Philip Leonard, and Joseph John Thomson were intrigued with explaining the photoelectric effect. Physicians using the electromagnetic wave-light model predicted that increasing light amplitude would cause an increase in the kinetic energy of the emitted electrons, and that an increase in light frequency would increase the current. Contrary to the predictions, the experiment demonstrated that the increase in light frequency would increase the kinetic energy of the emitted electrons, and the increasing light amplitude would increase the current. It was until 1905 when Albert Einstein successfully explained the photoelectric effect based on the proposition that light behaves as particles of electromagnetic energy called photons. These photons contain a fixed amount of energy, quantum, which is dependent on light's frequency. Concepts. Several concepts must be clear in order to understand how photoelectric effect works. First, energy E is produced by the photon is directly proportional to the frequency of a photon. Therefore, increasing the number of photons will not have an effect on the energy of a photon. This can be proved by the following equation. The energy of a photon is equivalent to H, where H is Planck's constant, 6.63 times 10 to the negative 34 joules per second times F, the frequency. Each metal is unique in that they require a different minimum amount of energy necessary to eject an electron from its particular metal. The minimum amount of energy required is referred to as the work function, W sub 0 of the metal. If the work function of a specific metal is not met, then the metal will not release any electrons. The photon must have enough energy to meet the work function, and the excess energy will be utilized as kinetic energy of the ejected electrons. Therefore, the kinetic energy of the ejected electrons is expressed as following. Kinetic energy max is equal to the energy of a photon minus the work function. Since the work function must be met in order for an electron to be released, it means that the photon must have a minimum required frequency to meet the required work function. The minimum required frequency of a photon is referred to as a cutoff frequency. Cutoff frequency equals a work function over Planck's constant. Now, some fun facts. In 1922, Albert Einstein actually obtained the Nobel Prize for his work in the photoelectric effect, and not in relativity, as most people assume. Well, actually, it was Heinrich Hertz who discovered the photoelectric effect. But Albert Einstein was able to explain it, unlike Hertz. The photoelectric effect plays a role in helping us understand light's relationship with the subatomic particles. As well, did you know that a photoelectric effect is employed in many of our new technology? Well, the following are just a few applications.
Okay, so an application of the photoelectric effect is in the case of solar panels. So what happens is you have your house here. These are the curtains. So the people that install the panels put them on your roof to maximize the amount of light that hits them, and therefore maximizing the amount of electricity, of current, electrical current produced. So this is your solar panel. So solar panels are made of what we call photovoltaic cells. They're called this way because the photo part is from the photons of the light, and then the voltaic part is it's associated with producing a current, and that current gets converted to what we can use as electricity to power uh, the devices we use in our homes. So this is your solar panel, okay? So you have light here. This is the sun. So what happens is this is okay, the sun emits energy in the form of photons. Photons are an electromagnetic wave. So the photons hit the solar panel, which is usually a semiconductor. What's mostly used is silicon. So the photons come here and hit this, and then electrons in the semiconductor are pushed outwards. And then what happens is a form of polarization happens within the solar panel because electric charges accumulate at the top because they're emitted here, and then positive ones accumulate at the bottom. And then this forms a current, which is then used to power all the devices in the house. Another further application is in the case of satellites. Okay, so imagine you're an astronaut and then you have the Earth. The problem with satellites, this is the satellite. The problem with satellites is how are you going to give it power? Okay, a lot of satellites, what their function is to keep everyone around the world in communication with each other. Okay, so it helps us all stay connected. So how does this happen? Okay, it's similar to the solar panels. So this is the sun. So a lot of the times what they use for satellites, the type of metal is platinum because it has a really high work function. So, okay, so this is your satellite. So you have, here's the energy of the sun, the electromagnetic waves in outer space, right? So they're coming in and they're going to hit with the platinum, the metal that's on the satellite. So what happens is the electrons are ejected, and then similar to the photovoltaic cells and solar panels, it's the same principle, but it's even further applied, not just for homes, but to satellites in outer space. So this is going to create a charge for the satellite, and that charge is what's essentially giving it power, and that power is what's being used to keep us all connected, or whatever the function of the specific satellite is. Another way that we see the photoelectric effect being applied to our everyday lives is in the case of elevators. So this is your elevator. Okay, these are the number of floors. 1, 2, 3, 4. Let's say this is a library there on campus. So let's say you have a person here. The person's coming in to the elevator because they need to go, let's say, from the 4th floor because they were studying. They need to go back down to the 1st floor to go back to class. Okay, they're happy. So the elevator doors are right here. They're already closing. He was too late. They're closing in, but he's walking in here. So instead of having to wait all the way until it closes, the door closes, and then let's say someone else is using it, so it's going to take a long time until he's able to get back the elevator to use it. Because instead of that happening, what happens is when he's coming in here, there's a sensor right here. I'll do a different color actually. There's a sensor right here, and then this sensor has a little, like a mini circuit within itself. So it's always emitting a small beam, a laser beam that hits down here. So when it detects that a person, okay, let's say this guy, let's say he's over here now. When it detects that a person is here, let's say their arm, what happens is this laser beam, instead of reaching all the way to the ground, it hits here. So this makes changes within the circuit right here to say, hey, it tells the elevator, hey, there's a person here. So it sends a signal back down to the elevator to say, okay, reopen the doors. So the doors are going to reopen, and that way it allows the elevator doors to open and the person to not be accidented by the closing of the elevator doors.
Okay guys, so we're gonna prove that the photoelectric effect works. So the elevator's closing, you put your hand, and then the detector there is detecting the motion here. So that's the reason that the photoelectric effect works.